Welcome to the Product Science webinar about mobile app performance engineering. I'm Steve, and I'll be your host today. Our mobile app development topic for today, scheduling network requests and how one can achieve huge performance wins without touching the back end. Product Science offers a new set of tools for mobile app developers that allows them to have instant and deep insight into the behavior and performance of applications before they are launched into production. We'll take a look at these tools later on in the session. This webinar is designed for mobile app developers who are eager to improve performance and user experience of their apps. Our agenda for today is as follows. First, we're going to review a bit of background about mobile app performance engineering and then get into the unique role that network requests play. And then we'll dive into some hardcore examples of various apps with network request problems and associated potential solutions, and then review how our product science toolset helps give unique insight into network requests. So here's a bit about me. Again, I'm Steve. It's a little bit of a quick glance about why I'm your host. I have a lifetime of experience bringing performance-oriented technology to market, starting with the giant systems of the internet like content delivery and video streaming and cloud, and arriving now at the most critical piece of a user's day, the mobile phone. I'm very excited about the opportunity to help improve user experience in an area that has been neglected so far by the market. We've asked many hundreds of mobile app developers about their performance initiatives. Most do not have them at all. The few who do haven't usually dived deeply into their applications using sophisticated tools. They wait for an alert from some kind of monitoring system or DevOps team or from the CEO, and then they take time to figure things out. Performance engineering is typically reactive. Developers make changes, do a quick check in an emulator, push to production, and then get back nasty grams from DevOps or that midnight CEO call showing performance alerts. The average time for addressing these problems measures out to be about a month. An app is pushed and it takes about a week for most users to update. Then it takes a week to understand that a problem is happening via the typical metric systems that are in place. And then another week is needed to fix the problem. And then the app is pushed again, and it takes a week for users to update, and this cycle repeats. This reactive cycle creates immense technical debt, bad development habits, and never allows for truly performant apps to emerge. We've examined mature apps that have been in the market for years, and they have user impacting performance problems that have been unsolved for all of that time. How does one break the chain? By understanding how an application works before it's pushed to production, by using tools made specifically for the development phase of an application's lifecycle, and exercising best practices for mobile app performance engineering. Let's first talk about one of these best practices, tracing applications with a code profiler. This is a flame graph. A flame graph represents exactly how the functions of your code are performing on a CPU, and it works by code profiling. What you'll see here is the name of a function as sampled from the CPU. In this case, it's MySQL daemon. This is a server example. And you can see that this function is executing for a while. And then you'll see some quick functions like a search or a select that are shorter. When you stack these up, they make a flame. So on the x-axis is duration, y-axis is function name. This was invented by someone named Brendan Gregg at Netflix. And this is the sort of industry standard way that code execution is represented for both servers and for mobile apps. We're going to take a look now at one of the banes of performance that will appear on a chart like this, network requests. So an obvious concern when designing mobile apps is that network requests are going to negatively impact a mobile app's performance and therefore a user's experience. However, many developers do not know about the secret life of network requests. Network requests linked to performance is not necessarily a back-end problem. The secret life exists within the app itself. One secret is that network requests have a huge impact on battery drain, and there are many different steps that one can take to minimize the impact on battery via proper software design. But the biggest secret is that despite dozens of solutions on the market that claim to help mobile app design by including network requests as a metric, none of these tools actually show you how the network request is behaving at a code level. They only show how long the network request takes. Therefore, they cannot help with the proper remediation of network request behavior on a mobile app until now. And we'll show you some examples later in the session. So at this point, you might be thinking, well, wait a minute. Why are we even talking about network requests? I work with a network and DevOps team to handle that. Well, the answer is that these are mobile apps. The app controls how it interacts with the network, and code controls the app. There are a wide varieties of ways that a better understanding and control over mobile app code can bring substantial performance gains and improvements in user experience without ever interacting with the DevOps teams or cloud teams. This is a complicated topic involving app architecture and solving concurrency issues, but with proper tools, this topic can be addressed. Most of the traditional tools in use by those DevOps teams are geared for alerting and measurement of very narrow behaviors like request time, but they are not geared towards a deep analysis of how code is interacting with the phone, nor will they suggest any solutions. So let's talk about secret number one, battery life. We've all been there on a plane or in a car or on a train or out and about and watch that battery indicator get lower and lower and lower the more we use our phone when not on Wi-Fi. And we perform that calculation of how much time we have left in transit or waiting or sitting wherever we are until we run out of battery life in a Wi-Fi free zone. And we all know instinctively that it has something to do with surfing the phone, but there is an exact correlation to the true cause of that battery drain, and that correlation after screen brightness leads to network requests. The phone's radio has multiple states, and the states consume a corresponding amount of battery power and are linked directly to network throughput. But network throughput and its behavior is under the control of the application. Switches of network application behavior lead to ramps in powering up and powering down the radio between different power draw states. And as mobile app developers, we all know or should know about techniques of bundling and efficient protocols like gRPC and efficient uses of caching, but the scheduling of network requests and how they interact with the rest of the application is just as critical, but is totally unrelated to communicating with the back end. There are now tools that enable us to see exactly how the network requests interact with threads and with other functions on the phone to give us insight beyond the simple lists of network requests that were available to us in the past. Now, there are many dozens of solutions on the market that use a back-end approach to help monitor a user's mobile app performance and give insight into how long network requests are taking in different regions of the world and on different phones and in different user groups. This brings us to secret number two. Monitoring data does help to get an understanding of how your app behaves out in the world. However, there's no actual code level suggestion on how to fix the problems that these systems discover. This is because the lightweight instrumentation that is compatible with a production environment can only deliver a one-dimensional set of metrics to a monitoring system and cannot truly profile and report on the actual code behavior of the application. As we will see later in this session, there are substantial improvements that can be made to a mobile app without any changes to the backend. Some of the typical metrics delivered by a monitoring system include response time, payload size, success rate, geographic location, network name, and can even have more than this. And that's all great. And it's really critical to know. But what about the code? What about how it's behaving with the application, in relation to the rest of the app's code? So some examples you'll see on this table on the lower left, these are two different vendors in the market. And what they will show for mobile app metrics of a network request: response time, payload size, success rate. That's some examples from vendor A, vendor B, errors on the screen, load time per object, event hierarchy. Again, useful, and it's critical to know that there's a problem, but what's even more valuable to know is how to understand and solve that problem. So to truly get to the bottom of mobile app performance, there are some key steps to take. 3 key ones that we'll look at today. Number 1, profile your app using the right tool for the job and to visualize threading and function connections. Number 2, study actions and reactions on the phone, what we call user flows, a click and a response, a fling and a response. And number 3, correlate these traces with a video or visual of the user flows. So let's do that now. In the bad old days, if you were trying to do this, what you're going to see is something that looks like this. You'll see a static flame chart, but it's sampled and it's going to be missing key functions that could hold the phone up. If you're using a web profiler, it's going to be empty. You're going to see mostly a white screen because the web profilers don't capture everything that's on that a phone can do. Or you might look at a list of methods in your IDE and it's not really human readable. So this is what we call the bad old days, legacy tools. Now let's leap forward to the present. And we're going to look at 3 different examples of real world apps that all have performance problems linked to network requests. The root of these performance problems are not discoverable via typical monitoring tools, which will only show lists of metrics, but we're going to use a new set of tools from product science that will allow insight into why a problem is happening and how to remediate it. The first example is Telegram, the messenger. So here we have Telegram, and what's going on with Telegram is that network requests are happening and they'd be listed on a monitoring system, but there are functions that are calling these network requests, and a typical monitoring system won't show how they behave. Like, what is the relation of these to the rest of the code? So what you're seeing here on this slide, and we're going to go live to the tool in a second, is the product science tool. This is the main thread. Here are those same kind of flame chart views of functions. There's a timeline on the top, but unlike web profilers in the market, you're going to see that there are full names in all of these functions, and you're going to see this yellow line. This yellow line is showing a function calling another function. This only exists with product science, that you can see not just that a function is executing, but which one is calling which one. This is new technology and is a total game changer for mobile app development. Now, what's happening here in Telegram, that we're now live in the tool, is that there are a stack of interface-related functions here, action bar layout, right, and a few others, chat activity, and they're making network requests. And you can see a choreographer here that's drawing the screen, but this entire experience is being blocked by a call of Chromium view in the middle. These could be resequenced to happen before, and this would enable the user flow to go by much better. And we're going to look at what a fix looks like in a second. So here's an example of only by visualization of the traces that come from code execution and seeing which functions call which, and having all the names there, can you understand how network requests are impacting a user's experience? A monitoring system would just show a list of these. It cannot show what is happening in the code. So even though this block is there in order to enable this chat to pop up, it's causing a 650 millisecond delay because of that Chromium web view and where it's scheduled. After a fix, you can see how it moves much faster. This is the ability to correlate video of the app with the traces. And you can see post-fix, a smooth move from the chat, from the users to the chat. What I'm showing here is the ability to correlate video of the application with the traces. This is unique to product science. So that's example number one. Here is our second example. What we see here is that there's a network request that is loading what is actually a blank list and causing a 150 millisecond delay. And although this network request would be listed on an observability tool, the impact of the user's experience and the interaction between the network request and the rest of the functions would not be known. The tool would just show on a list that there is a network request. So the ability to see how this tool traces across the threads, the tool will show the different functions and how they go across each of these threads on the left. Here's the main thread. Here are the rest of the threads. This is unique to product science. Now, if we look at this example here, we can measure to see this delay between an initiating function and where this blank list is being called. So this is an unnecessary list that's coming up that's halting a user experience. And you can see there's a network request that calls it right here. This again can be reordered so that the user flow can move along and give the user a better experience. In our third example, we have two repetitive network requests happening one after the other, yet there's no difference in the user's experience that is happening while these network requests are in effect. This is a classic example of legacy behavior, something that might be there for years that may be slowing down a user flow, and when on radio, draining the battery unnecessarily. An observability tool will show the requests, but it doesn't show the context that these are duplicative and happening one after the other in the stream of functions as they go by, blocking a user flow or making unnecessary calls to the back end. And you can see them here. Let's go to the tool again. So this is this example, and here they are right here, one after the other. They're identical, these stacks. So in summary, we have some great learnings here. Okay, example number one, Telegram, an improperly scheduled network request, which is tanking performance. Scheduling the network requests before the initiation of that Chromium web view could save 650 milliseconds of time. And we've actually made a fix on that. That is demonstrable. Number two was an improper network request that was rendering a screen unresponsive, pulling up a blank list. So this is missequenced and is causing delay and a bad user experience. This is easily able to be remediated by having the network request do something useful or by refactoring the UI so that the user flow moves on while whatever is needed to happen on the network happens rather than a blank list. Example number three, legacy code, repetitive network requests that they may be needed, but probably not, because they're doing the same thing right next to each other, but the user flow and the experience has not changed. So this is something to be investigated. All of these issues regarding network requests are examples of behavior that's happening that can be found in pre-production, that monitoring tools might show that there's network activity, but not if there's a problem and why. A better tool set is needed to see how the code is behaving, and so enter product science. So let's hear about this from a customer, Rally. Rally is a platform for buying and selling equity shares in collectible assets. They have everything from sports memorabilia to artwork to vehicles. And if you've ever dreamed of owning something as cool as a 1980 Lamborghini or a 1953 Topps Mickey Mantle baseball card, then Rally is a great place to buy a share of that kind of asset and enjoy your ownership while having an equity stake. We're going to hear from Akshay Bharath, who's a lead iOS engineer, about product science. Akshay, thanks so much for joining. Really appreciate it. We've really enjoyed working with Rally over the last year. I love the platform. I love the ability to have a share of a cool asset. We're talking about network requests today and how sometimes you can see them, but with better tools like product science, you can understand them. Tell us a little bit about your experience.
Yeah. Hey, Steve. The thing about, I guess, just in general, network requests and sort of analyzing some of the issues that can happen from an iOS perspective, right? Yeah, certainly you can kind of hit some of the issues where you see hangs on the UI when you're sort of interacting with the app with certain views, but it gets tricky when the code, like our code base is a couple years old. You have several layers on the networking side, and you just have to kind of figure out where the networking issue really is when we're making multiple different kinds of requests to different endpoints. And so it's tricky to like really pin down requests that are taking long or blocking the UI thread, and it just gets tricky. So I think with the product science tool, it's made it so much easier for us to sort of take a look at the call stack, take a look at what's going on in certain sort of core flows, and really isolate issues that are happening, not just on the networking side, but really anything that's happening that's causing things like hangs and causing issues that the users would just be stuck with and wouldn't really be enjoying from a user experience. It's really easy to sort of isolate that and see it and pin it down from the tool.
That's fantastic. And we know as apps evolve and get refactored, these things can sort of creep back in, and it's good to have a way to keep an eye on that. How does this help sort of improve relations and the ability to work with your backend team or a DevOps team?
Yeah, it's a good question. I think it helps us, take the data that we have. We can look at the tool and be like, hey, here's like the call specifically, or calls that are taking a while to come back, and we can take that information and show the backend team, hey, here's the call we're making, here's the endpoint, here's how long it's taking for us to get that response, and it's really affecting the experience of the user. So can we figure out what's going on in the backend? Is the payload really big? Is there something else going on? And really help us sort of pin down a specific endpoint or endpoints that we can then kind of improve, and they can sort of take a look at and improve it. We don't have to just be like, hey, backend team, something's wrong with the backend, can you help us? We can be very specific and show that endpoint.
Right, and show how it relates to sort of the threading and the code, and how like what may be okay for some things in a mobile app would be different, and you can show with the product science tool how that, how it works with other, parts of the code. So I'd say my just last question of the day would be, onboarding developers and, learning to understand an app and having deep insight is always sort of critical, because you want to get new talent and you want to refactor. How does a tool like product science help when it comes with onboarding and giving insights to an app in ways that other tools you've seen do not?
So from an onboarding perspective, I think it helps new engineers just sort of understand the code base on a different level. Like they can sort of take a look at what's happening under the hood. They can easily separate out the threads. They can see what parts of it are taking long, what parts of it are sort of hanging up without like trying to put in the guesswork. You can kind of see it. You can kind of visualize it. You see the video. You can step through it, go backwards. It really helps you understand what's going on in the code base, especially as a new engineer coming in who, they're going to look at code that could be, many years old. There's multiple layers, and it's going to take them a long time just to sort of step through it, maybe just through Xcode. You can use product science to really get a visual of what's going on and sort of formulate, get like a mental model of like, hey, these are the threads that are doing network calls, or here, there's other things going on, and there might be improvements, optimizations that they could think of right off the bat, even as someone coming in fresh.
I love it. Thanks so much. I really appreciate your time. I've got my eye on that Lamborghini, so I'm going to want to be getting some shares of it. Have a great day. Look forward to working with you in the future.
You too. Thanks so much, Steve.
Let's take a look at this photo app. User taps preview to open a photo. There is a noticeable delay between the tap and the photo being fully loaded. But don't worry, product science can help reduce delays like this one. To make this possible, we record traces of your app. When your app is running, thousands of functions are executed. We record these functions and place them on timeline next to the video recording of your app. Now we can clearly see the cause of the delay. In this example, the render image delayed due to scheduling on the main thread and waiting for unrelated processes to finish. With a small code change, the function can be scheduled to another thread. The unnecessary delay is gone.